funny. So yeah, we'll get started. First thing we're going to do is address a little bit of the summary for today. We forgot to delete this, but don't worry about it. So first, Ben's going to talk a little bit about the overview of our control system.
Okay, so there are two modes. So the first one I'll talk about is the teleop control. So we have the driver station phone here with the controller, and it can communicate with the onboard phone, which acts as the CPU for the robot, and that's over Wi-Fi direct, so as you can see here. And then we actually deploy our code to the robot controller, which is the phone on the robot, and then that sends instructions and commands to the Rev Expansion Hub, which can distribute power to different motors, and we can also get feedback like from sensors like the gyroscope and encoder counts.
So these are the, what's coming up next slide, right?
Yep.
Okay, so this is the Rev Expansion Hub. They're going to talk about it, but I'm going to put one through each side of the room here, so that you can see it.
Do you
Pass
want
it
those
around.
Yeah, you want them back?
Kind of want them back. So those are $175 each.
I know.
So it's a high entry fee, if you like, compared to what a lot of us in hobby are expecting to put out. But it's also very, very plug and play and very easy to use. And we've ended up converting all of our stuff. Huh?
Greg's a nice guy.
And Greg's a nice guy. Yeah. You get your value for the money on this one.
So it's got like 2 motor drivers in it?
It's got 4 motor drivers in it. Each one has dedicated encoder tracking, and it's got. Are you guys going to run through the whole thing, or not?
We can real quick. So
Yeah.
these are the 4 motor ports, and if you see these small things, those are encoder ports. Down here are servo ports. There's 5 servo ports per rev hub, 6 per rev hub, so you can have a total of 12 on your robot because you can have 2 rev hubs. And along here is also a bunch of other sensors that we can use, like I2C sensors.
So there's analog, there's digital I/O. This is a 3.3 volt system. There are 4 separate I2C buses, independent, on each one, and then there's some UARTs and RS485, maybe? I don't remember. Yeah, it's bi-directional, and that's what you use to daisy chain them. The competition allows you to use 2 of these, but you can actually daisy chain like 128 if you want. Assuming you were satisfied with the communication that happened on that bus with that many devices. But that's what you get in a single one of them, plus some 5-volt power takeoffs. The servo ports are only 5 volts. They're not 6 volts, but you can get a power injector to take them back up to 6 volts.
That's all.
Okay.
Okay, so yeah, again, there's the wiring. So the robot controller, which again is the CPU, is connected by USB to the rev hub. And then as you can see here, you can wire the motors to the motor ports. We use a 12-volt battery, which just connects here. And then we have our I2C sensors, analog sensors, and our servo.
So the sensors, at least the ones that Rev produces, are generally pretty reasonable. So they've got a time of flight distance sensor. We've got 3 of them on the robot. That is like $18 for the sensor. It's a common chip that I think a lot of you have looked at.
ST Micro. Yeah, like
ST Micro.
Yeah.
Max.
Yeah.
I don't remember the exact model number.
Yeah.
Is it the 3-meter one or the 1-meter one?
This one does, they advertise this as being capable of 2 meters, a minimum of 5 centimeters.
Okay, I think that's the first version. Yeah, okay.
Go ahead.
So there are some slight performance issues that do arise from this. So like things like, so first of all, the Rev Hub operates on commands, which is provided as an API in the SDK that sends commands from the robot controller to the Rev Hub. These commands are pretty expensive and they can take a lot of time. So ideally, you would like to consistently get a lot of data at once instead of querying for each specific thing, like different encoder counts, readings separately. Some sensors like the IMU use I2C communication, and it utilizes a hardware bus to establish 2-way communication, but the problem with that is that it's pretty slow, and slow I2C communications mean like less updates, and we like to use, for more advanced autonomous sequences, it's nice to be able to measure our angles and measure our encoder counts, and if those are coming slow, that means that our post estimates will be less accurate.
So by expensive, you mean they just take a lot of time?
Yeah. So
Compute is not the primary problem here, even when we're doing vision stuff. It's really, it's more the whole Android subsystem combined with how it communicates over the USB bus and then perfuses, if you like, to the other smart sensors on board. So it's that update cycle that is the only thing that's really in our way from, like one of the things, so there have been some improvements in the last releases of both the firmware and the SDK, where they're bundling a lot of those updates on the USB bus together, so it's happening faster now. The last time we tried doing balancing on one of these robots with the system, we weren't at quite an update rate that we needed to. We might be able to do that. That's actually a goal for this platform, is to figure out how to balance into wheels.
So is it, do you notice like a significant delay, like you do something and it just, you know, takes like a fraction of a second to actually do something, or?
So the place where it's more obvious is, so we have this driver station and the robot controller, and the telemetry gets sent to the driver station. So the robot's trying to always send data over there. And when we're in a teleop mode, that's where we've had the biggest, most obvious performance issues. I mean, we've had lags as high as 22 seconds. At times that was at Worlds last year, when the entire stands, you know, there were thousands of people in this one. There must have many thousands of people in this one building, right? And all of the robots are using Wi-Fi as well.
And not only this,
Right?
we're FTC.
And it's just crazy.
And not only that, like we're only FTC, we're in one hall. There's also 5 other halls running robots too, all of them using Wi-Fi.
So that is a worst case scenario, and yet it's our World's competition, right?
Yeah.
But once you get to, if you're doing just purely autonomous stuff, then it's only the updates that it's sending out, and it's not actually blocking on those. So the stuff that's happening locally is going to happen still at a pretty reasonable rate. But again, when we say it's slow compared to like when you're doing real-time stuff or you're doing a completely dedicated microcontroller, you're not running the entire Android stack. You know, there's so much else happening on an Android phone. We're the first ones to acknowledge it's not an ideal thing for, like, you wouldn't create a space probe built on an Android phone. However, it is incredibly convenient when you're just doing regular app development, you know, and you can always think of like, this is the prototyping version of what you want to do, and then if you want to create a hardened, guaranteed execution kind of environment, then that's something you can do after you sort of figure out all your sensors and your robot logic. All right.
So we're gonna talk a little bit about our actual robot. So I'm gonna power it up real quick. So a robot has a bunch of things we call articulations. Articulations are basically what we use to control the robot during regular match play. So the bottom thing right there is called sizing mode. This is sizing mode. Sizing mode is what we use because our robot has to fit in an 18-inch sizing cube at the start of every match. Now, when
So it will actually be hanging from the hook at the beginning of the match in that configuration.
Nice.
So we can't show you on this because, you know, it's not big enough. But so it starts off like this. When match play starts, we go to a position we call safe drive. This is, oh no, that's not.
Oh, demo attack.
Demo fail. Get out our first one.
Won't be the last.
It won't be the last.
I just gotta hope this doesn't happen at championship.
Now, was that because it was anticipating something being in front of it? Was it anticipating a ladder being in front of it?
Probably not. I think he was probably just ready to fail mode.
Oh no, it was just a bad start.
Oh, it's just a bad, we do it, so there's, when we get to the, sort of what is called an op mode and how we do the life cycle execution of the robot program, you'll notice that there are separate stages. So there's like an initialization phase when you're not expected to be moving, and we didn't set up that. During our initialization phase, we need to make sure that the robot is just quiet and stable and in its proper configuration and level. Right, because we're calibrating the IMU and
I
things like
gotcha.
that.
Okay. Okay, so this is what we call safe drive mode. A lot of the reason why we have articulations is because we have to balance the center of gravity on this robot. The lift is almost as heavy as the drivetrain, or it's like a significant
Excuse me.
weight compared to a drivetrain, which is why when we're moving the arm around to weird positions, we sometimes have issues with the robot not being able to drive or the robot tipping over because it's not able to recover from the fall. So this is what we call safe drive mode. This is what we're doing when we're navigating to the crater where we need to pick up our minerals. Those are what we call the minerals. So now if we're supposed to intake, there's normally a crater around the minerals. We press B once and we drop to the pre-intake mode. Pre-intake mode lets us rest right on top of the crater where we need to go inside. If you press B again, we rest and push down on the ground. This allows the robot to move very easily. So now I can collect the minerals. Let's see if I can pick up this up.
And he's not our driver, Korean's our driver.
You should probably do that. So there's 2 minerals being picked up there. Now if Karina
And
presses,
there's a rule that says you can only handle 2 at a time. So if we had an extra one, it would be a fault, or a penalty.
so now I'm going to be pretending to be the lander. The lander is usually something that's behind this hook right here. The lander is where you drop off the minerals as well. So if you press the B again, it goes through a whole sequence where it sort of sets itself up to come to the lander. And now she can drop the minerals directly to the ground. Our thing is broken, so there's a reason. But yeah, so that's the normal match play mode. Now when we go to the end game mode, can you hit
And
safe
to be
drive?
clear, we started out earlier in the season where the driver had to learn to do all of these things. Manipulate that Superman, the thing that pushes it up, as well as the elbow and the distance that it was going, all at the same time, and they're all messing with the center of gravity of the robot, right? So these articulations automate the transition between these set points.
Yeah, so now during the end game, we have to get back onto this last thing, right? Now Korean can sort of demo it, as long as I catch it. Go ahead. Notice how it goes very slowly when it's lifting that arm up. It's because it needs to not tip over. We've had it tip over so many times during the matches, and it's just bad. So now as she gets closer, she can press B once again. Get to, now I'm going to move it forward physically. Oh. No.
Here, B.
Hey. So now she can lift up the elbow, make no override. And she's up the ground.
So at the end, you only have to be just visually clear of the ground. You don't have to be throwing shit up. And you got 2.5 minutes to do that whole cycle. So that includes a 30-second autonomous at the very beginning, which we haven't really explained very well, other than getting off the lander. And then 2 minutes of teleop drive with the last 30 seconds. The rules change a little bit, and that's when you can go for the lander.
So before that last 30 seconds, this is the traditional cycle that we go through. Safe drive, go inside the crater, pick up some minerals, press it back up, and deposit at the lander. Then we go right back into our next cycle. So that way you can continue to pick up minerals as fast as you can. Right now the best teams in the world are at 22.5 cycles, which is about 55 minerals.
In less than 2 minutes.
In 1 minute 30 seconds.
1 minute there.
Yeah, in 1 minute 30 seconds. We're nowhere close to that, but you need to go really fast, right?
Are they throwing then?
No. Throwing is illegal in the match.
So they did partly the smart thing where they have 2 separate systems. So one is just responsible for going out and gathering the minerals. Again, you can only control 2 at a time. So you go out, you gather the minerals, you pull it back real fast, you do a transfer into something that sends it up. The minute you do the transfer, you can go back out and position the intake one while the other one's dropping. And the minute you let go of the ones up there, you can actually start intaking over there and start the whole cycle.
So they building like
They're
a
like
conveyor
doing
or
this.
something?
Huh?
Are they
2
building?
conveyors that are working
Okay.
together.
Okay.
It's a typical approach. Yeah.
And there's also teams who do similar arms like us. They just have a stronger base, so they don't need to like lift themselves up or anything. They just,
Okay, so how do you have plans to get to 22.5?
Yes.
There's no way that this platform is gonna get to 22 and a half.
No, that's
It's
what I
just
was-
not-
that's
you-
what I was
You
figuring.
can model the best case cycle once you can see that we're not quite where it's really silky smooth, it's
Yeah.
smooth as fast. But we're gonna get there, and I think we're gonna be at like, probably 15 cycles, by the time we're done. One of the ways we explain our approach is, it's less about just rigorously trying to defeat the game, which is probably what you should do if you're a purely engineering kind of thing. But this is a high school, and our approaches to sort of just stretch our boundaries, right? And so with something like this, we're taking on a little bit more complexity, just for the sheer joy of dealing with it and learning from it. And it's probably not gonna make us the highest, the greatest competitor. But there's also a whole set of awards behind this thing, and so we're focused more on like the innovate kind of stuff and the design stuff.
Gotcha.
So eventually I think we will get to the point where we're competitive during the game, maybe not 22.5 cycles, but somewhere up pretty high.
We want to at least be in 2 digits.
So,
Regularly.
You may wonder, like, how are we able to control these things completely autonomously without the driver having manual overrides? And we just employ some pretty simple control loops. And the control loops they're PID based, and they ensure that the robot slows down as it gets closer to the set points. On our articulations, since they don't need to be quite as accurate, the Rev Hub has built-in PID gains that we can, PID and feed-forward gains that we can employ. But for the drivetrain, we do have a custom PID controller that we tuned ourselves that helps us have accurate turns, be able to go set amounts of distances consistently. We would also like to maybe improve that and maybe tune our coefficients better and maybe add like feed-forward turns to help increase accuracy.
So now we're going to talk about a little bit of the autonomous part of the match. So before we go into this, I'll sort of explain what happens during autonomous. So first thing you do is deploy from the lander, and you let go of the latch. You saw how we latched on, just the opposite of that, the D-latch. Then you have to do something called sampling. Basically what happens is there's 3 minerals set up on the ground in different configurations. We have to be able to detect the gold mineral and knock the gold mineral off. And now that requires a little bit of computer vision. Arjun will go into how exactly we do that. After you do this, you also have to deploy something called a team marker. So you have to navigate to a different place on the map and drop off our sort of like our team marker. We don't have it with us right now, but it's like a small duck that we use for our team. And then we come back and park in the crater so we can start our cycles during Tilia. So now Arjun, go ahead.
So for us to be able to navigate through the field, we have a robot, obviously, and we need to be able to go to certain coordinates on the field precisely. So normally what some teams will do is they just have the robot drive forward for a set amount of time, then turn for a set amount of time, drive forward for a set amount of time. But the issue behind that is you're not going to be able to take into account for real world feedback. So say your wheels start skipping, or say you're unable to turn, or maybe your battery is low, so you're not able to move as fast, and that could cause serious issues. So what we do is we use encoder feedback in order to make sure that our robot can consistently do the same thing over and over again. So every iteration of our control loop, we read in all the inputs from our sensors. We take in our IMU value, which is the current heading of the robot. We take in the encoder values of each wheel, and then we put it through our PID control system to figure out exactly how much correction we need to do and how much motor power we should send to every motor. So we have to have this alternating cycle going as fast as we can, reading in sensor inputs, then putting it into our PID loop and outputting corrections, and then doing the entire thing over and over and over and over again. So this thing will happen multiple times per second. I believe we have like, I think 10 times per second is our loop time. So, autonomous issues. So
That's from a ways back, it's probably faster than that now.
Yeah, I was gonna say,
We've done profiling recently.
Yeah.
You can do balancing at 100 hertz, right?
Yeah.
Pretty easily.
You just let it loop as fast as it can, or do you kind of time it so it's consistent?
We have no control over it, that happens
That's the
under,
input.
that's the underlying, yeah.
I mean, we can add loop control to it, but there's no need to. I mean,
okay, because a lot of times
What we
with,
can do is we can evaluate how much time has elapsed between each loop. We don't have control over when that happens.
Yeah, but you can
But
estimate.
we adjust our PID based on the amount
Okay,
of time
yeah.
that it has elapsed.
yeah, because you have to adjust your coefficients based on your time of your loop. You know, if you doubled your loop time, you're gonna have to have your coefficients, I believe. I
Well, we
believe
don't
that's the
actually
right
have
way.
to, the coefficients will stay the same regardless.
Okay,
Because we're actually multiplying by the loop time.
okay.
So whenever that
Yeah, well, that's the
changes,
same,
it-
yeah,
it's sort of-
okay. It's a scaling,
Yeah.
yeah.
So there's a couple issues that happen. I mean, there's so many functions that need to happen in autonomous, and we need so much sensor feedback that loops simply won't work. We have because loops are blocking; they block other sensors from reading inputs, things like that. So we fix that issue through state machines. Now there's two types we have, and Arjun will explain that.
Okay, so basically, the idea behind a state machine is when we're going through our alternating cycle of reading in sensor input and then performing corrective action, we need to have the corrective action is going to be a sequence of steps, such as move forward 5 meters, turn right at 40 degrees, move forward another 4 meters.
These guys are gonna know what state machines are, so it's more about just our
Okay.
implementation of it.
So basically, what we have is each action is just a state in our state machine, and our state machine keeps track of exactly where we are, and at every alternate loop, we have one cycle of grabbing data from the sensors and one cycle of pushing correction.
So this is our depot side sample. There's two sides to the lander, and this is our autonomous for the depot side lander. So in auto setup, we have the basic mineral detection and pushing, things like that happen. And then it turns left, or based on the path that it sees, whether it's left, center, or right, it navigates through a different autonomous path, and at the end, it just stops near the crater.
And notice how easy to read this is. I've always been saying that because our code is so clean, we can even have non-programmers write autonomously.
So what, the prior implementation of this was all with switch statements, and you get many cases, and you forget a break somewhere, and you know it's the traditional issue with Java or C derivative languages, and so this is using Java 8 Lambda expressions to sort of make it simpler.
So when you say it's non-blocking, is it non-blocking in the sense that you're queuing up moves, like move forward so much, rotate so much, move forward again so much? Is
That's
that
correct.
Yeah. Okay.
Yeah, and so once you're in a certain state, so states basically have, they have to have a way to exit, right? I don't think we didn't put any of our state machine diagrams in here?
Oh, no, we didn't.
No, okay. There are legal transitions from one state to other states, right? And if you're doing behavior-based robotics, then there can be things that interrupt your current state. But all of that can be done with just general state machine logic. And so we have exit criteria for a state that will either move it to the next logical state or shunt it somewhere else.
So these are all Boolean based. So as you can see, there's some trues in there. True just means advance to the next state, right? So each of these methods that we wrote is a Boolean return. So for example, in the rotate IMU method, it will return false until it reaches 39 degrees. With the drive forward one, it will return false until it reaches the target distance. So we use a complete Boolean method, including those collector methods at the bottom.
Right, so, yeah, we already mentioned this, we're using Java's Lambda syntax.
Yeah. So we'll do a little bit of recap of computer vision. We mentioned it last time, but yes.
So, last time I believe we talked to you all about this, so we need to use computer vision for a part of our autonomous where we're sampling between 3 minerals, because the robot game basically says that we have to identify which position the gold mineral is in. It could be either on the left, as it's shown in the picture, it could be in the middle or the right, and we have to move only the gold mineral, and we get points for that. And if you move the wrong mineral, then you lose points for that. So, and this has to be fully autonomous, we can't have any driver input.
So there are actually 3 cameras on this robot. You can, you got an Android phone, right? So you've got 2 cameras right there. If you position your phone correctly, and you were using the Android phone earlier in the season, you can also add webcams. And so we're running off of a webcam now. And so you can have as many webcams as you can support with your hub and your power requirements.
Oh, wow.
So we're using a Logitech, forgetting which model it is.
It's C920, I believe. You have a slide on that.
So and that just plugs into the Android phone and the.
There's a USB hub thing that we have. We just
Yeah.
plug that into our phone.
Okay.
Yeah.
So you can either connect your Android phone to the Rev Hub using just an OTG kind of conversion, or you can hook it up through a regular USB hub.
Huh?
And it probably needs to be a powered USB hub, so that's what we have on
Yeah.
board, and that lets you plug in extra things.
Is the robot?
And so when there's a USB hub on the cart pod, it doesn't even have to have the driver station. We've also built a way to override it so that it's not expecting control from an external driver station, but you can plug in a joystick as well directly.
Alright, so, yeah, we already talked about this, so basically we need to figure out how to determine which position the gold mineral is in.
Now, go back. So the thing in the back is what we call the crater. So there's a bunch of noise in the background. The sampling minerals are the first three in the front. So, yeah.
So we've been developing 3 different parallel vision tracks. So Opencv is basically a collection of vision tools. It lets you combine them into pipelines. Then we've also experimented with using our own convolutional neural network that unfortunately didn't pan out as much as we hoped. And then the FTC app provides a built-in TensorFlow model, and it's intended for all teams to be able to use it. Unfortunately, it's not very effective, and we found it to be pretty weak at different lighting conditions. So we wanted to develop a way to interchange these pipelines, these different vision providers at runtime, so we could develop all 3 at the same time. So this is what we made for our convolutional neural network. We took a whole bunch of training data photos, then we wrote a program that will help us label them and resize them to the correct format. And then we started training a TensorFlow model with them. And unfortunately, we weren't able to get good accuracy just because we didn't have enough training data. And so this is our Opencv pipeline that we've been working on. So Opencv is, again, a collection of tools. So what we did is we did an HSV threshold, and it just takes all the yellow blobs in our image. And then from there, we look for contours that fit a certain criteria, which are of a certain shape, certain ratio, minimum area, maximum area, and approximate position.
So you're discriminating by color first
Yeah.
and then size afterwards, yeah.
Yeah, first we discriminate based on color, and then after that size and position, and we're just picking the best fit contour.
So are you using the fact that the ones in front will be lower in the screen?
Yeah, that's part of it.
That's what you're using?
Position on
Okay.
the screen, yeah.
Yeah,
Okay.
and bigger.
And they're bigger.
And
Well,
they're
not
bigger.
necessarily bigger
Yeah,
because
you could
depending on
get
how
the
those
bigger
blobs in the
blob in
back
the
Oh,
back.
yeah. Made
They can look like
large.
one giant mass.
And we
Yeah.
have had issues with that in the past.
Yeah,
That's why you just point a webcam a little bit lower now.
yeah.
So there's a lot more of the pipeline. I think
Well,
we're gonna
hey,
actually-
now the question I would have here, okay, so you decide, earlier you were talking about that you were having issues with AI. I don't know if you were using TensorFlow.
Yeah, we were using
You were? Okay. And you said that you'd probably end up using Opencv probably with a blob detector, which you got. So you did end up going that way.
For now, we are, because we didn't have enough training data
Yeah.
to train our model. I mean, we might try it now that we're a little bit in a more grace period before Worlds. I mean, still have got a lot of work to do, but we might try looking back into TensorFlow a little bit, but we simply didn't have enough training data.
But this works, right?
Yeah, this works.
This works really good, right?
Consistently for this particular
Yeah,
challenge and these,
Yeah.
and these elements. If it were a more complicated vision or object detection kind of a thing, then this approach probably may not work.
Okay, now,
And we would-
let me ask you this from your training things that you have control over and things that you don't have control over. You know what color the floor mat's gonna be and the crater blocks?
Yes.
And but you don't know about you don't know about what's gonna be in the background.
That's correct, yeah.
All right, so in the training issue, if you blocked out the background with a solid color, say a blue tarp, okay, and then use your CV to get your just to get your training
You don't
things.
wanna clean up the signal ahead of time.
Yeah.
You wanna let the neural network sort of figure that out and include it.
Well, I'll
That's
give
my
you.
experience.
I'll give you an example of some issues. There's several of us working on donkey cars right now. And we've seen this twice now, where a person trains this donkey car to go on his track, and it works great. And then essentially, he trains it again without the track, and it works the same. And the reason for it is because it's picking up all the, like, okay, I see you sitting in that corner. If you don't move, every time I see you in the image, I know kind of roughly where I am.
Oh, right.
Yeah, yeah, so-
Sure.
Yeah.
But that's, well, I'm not sure about, I haven't looked into Donkey Car yet.
Yeah.
But yeah, it's probably learning positional placement from all of those things in
Yeah.
that particular room, and if you don't rotate the field or something like that, then it'll become sensitive to your specific training environment.
And
Yeah.
we did,
I completely get that.
we did try to train on all four corners of the field, different lighting conditions.
Mm-hmm.
We took about, I think we had a total of 200 images. We took like 50 in each corner of the field. And about 1/3 of those were from left, 1/3 from the middle, 1/3 to the right.
But I think we're talking about two different things, possibly, I'm not sure.
Okay,
but
200
one is-
images sounds like a small,
Yeah.
really
No, that
small
was too-
training.
Too small, but
Yeah.
going back to your sort of example, I'm not sure if we're talking about different kinds of things, so we're talking about discrete object detection.
Yeah.
Regardless of where it's placed and
Yeah.
what its background is.
What I've
As opposed to sort of a positional awareness in a larger space.
Yeah.
So I'm not sure if that's what you're.
Well,
Donkey
okay,
Car is, but-
I've been playing with Google DIUs,
Mhm.
little thing, and on that one, the training issue, what they do with training is they clean up try to clean up the image, but they vary the background of the image a lot.
Yeah,
So what you can
So,
do.
so you don't get like tuned into a background.
specific background, yeah.
Yeah,
Do you get
That's
blur in
true.
the background?
Yeah, I mean, so you can train with some images from a different background and like mix up the backgrounds a bunch, but the whole idea is like, we're trying to start off like this because that's like the real competition scenario,
yeah,
right?
that makes sense.
Yeah.
Yeah, but I mean, do you stir the pile is I guess what I'm saying, you know? Not just move the 3 blocks in the front, but
Yeah,
stir
it's
the
like-
pile, you
Right,
know?
Exactly, yeah.
So, Arjun, on there right now, the camera's actually working right now. This is what we use called FTC dashboard. It allows us to see what the camera is seeing. So as you can see, we split up the images into 3 different locations. On the left side, we see silver, gold in the middle, and silver on the right as well. So our program will tell us that it's a gold mineral in the center. Now, Karina, if you can shuffle up the minerals, you can see the actual detection of the gold moving with it. So if you move silver to the middle and gold to the right, and it's still detecting gold here. It's creating a box around it.
I don't know if you can see it, but somewhere there it says gold detection right.
Yeah.
Against the background, I guess you can't really see it.
Yeah, and
Oh,
here
yeah.
it says left, right here. I mean, it's not
And
very.
for their autonomous program, they just need a single good solid sample, right? And then they've got preset paths that they're gonna follow based on whether it's left, right, or center. Because we always know the position of these things, we just don't know which position has the gold one on it.
Yeah, it sounds like the way you're doing it is the right way, because it sounds the most robust way.
Yeah, I mean, what my original inclination was to have them do tracking all the way up to it,
Yeah,
right? But then you gotta worry about keeping it in frame and
Yeah, the frame rate.
and the frame rate and things like that. I mean, you can see that we've done tracking like that. This is, when we do it on a CartBot, that's basically the same kind of system. I mean, it's still Android phones, it's the exact same Android phones as what's on this robot. So it's certainly doable to do
Yeah.
live tracking.
Can you guys use like the Google Coral USB accelerator?
I haven't tried that.
Wait, what is that?
The new one that just came out?
Yeah,
Yeah.
yeah.
Wait, what is it?
Haven't heard of that.
It's supposed to allow you, to bring kind of what I guess they're calling it AI to the edge. It's like you don't have to, and they have a development board that you can actually snap photos associated with something and not have to do, all kinds of computation on a more powerful machine and then.
Well, we're not allowed to bring
can have
any
multiple
extra
CPUs.
processors to this.
Oh, okay.
Only
Right.
processor is the Android phone. That is
Oh, okay.
We can't even use we can use sensors that have, almost all sensors have their own smarts on them right now.
Yeah.
Like a time of flight sensor. But if we try to actually use that, then we would be illegal. Like,
Oh,
if we
really?
tried to use the onboard sensor on allowed sensors,
Yeah.
onboard processor, then it would be illegal.
So in this, we kind of use that for, the 6-can and can competition to find the orange cans, steer to them, and pick them up. Is your frame rate that slow that you can't use it to?
Have a frame rate?
No, we can.
Oh, you can? Okay.
We can. So, in fact, I think we ran a can using this 2 years ago.
Oh, did you? Yeah.
Yeah, there was one that we did, it was like the one that sort of tried to toss the can.
Oh, yeah.
Okay.
But it was basically running Android, that one was running Android.
Oh, okay, yeah. So is this even part of the, is that a requirement? Are you just supposed to locate it in one of the 3 zones? Are you
For
supposed to
this,
actually?
No, you
this
have to actually move
particular
it.
rule set,
Yeah.
this particular game, that's the way it was constructed.
Okay, so you have to move it or
You have to
So
move
we
it.
need to actually move the gold one and not touch the 2
other ones?
the balls.
Okay, let's see you move it.
Not touch the balls. Huh?
Move it, move it.
Oh, we don't have our auto stable. Oh wait, actually we can.
It's stable.
Yeah.
Oh, we just need to stop it immediately.
Here, I'll just be the lander.
Oh shoot, it's gonna try to deploy.
Yeah.
I wish.
I'll be the lander.
It should actually, could work. Try it out.
All right.
See what happens.
Okay.
No.
Remember, it thinks it's vertical at this point, hanging on the latch.
Right. It's only endangering children.
Yeah, it's like.
B for-
They signed a waiver.
That's right. That's why we had to start. Just cover yourself, Bobby. It's gonna come up.
Have an auto that doesn't do delatching.
Huh?
We need to have an auto that doesn't
It's
do
okay.
delatching.
Put in state 1.
State 1. We need by state 1.
Wait, did you press B?
All you need is one
Yeah.
fat loop.
I didn't.
You'll learn.
Okay.
Let Karina do it. She knows how to do
Yeah,
it.
give it to Karina.
Okay.
Give it to the expert.
Okay, you got it. What?
Oh, you're good. Okay. All right.
State 1. Oh, state 1. Right. never mind.
Oh wait, no, the slide's gonna go out.
Okay.
Yeah, it's gonna go
Okay.
Hold it from the hook.
Yeah, you don't,
Hold it from the hook.
you don't have to go to the gym, you can
It's
just
gonna
hold that.
Oh my god.
I know.
Okay.
It's not gonna do that until as
Do
soon
it.
as it's down.
Okay, here it goes.
Score.
Right, let's see if it samples.
It wasn't the right distance.
Yeah, the distances weren't set up right, but it did detect it.
But he wasn't as geometrically accurate as the lander is.
Right, right.
But, so, yeah, that would've, again, that's where, if it was doing live tracking, it would've corrected it that way.
Right.
But it's not, and but that means we're dependent upon the initial alignment being
So-
exactly right.
This is actually the picture that it saw when it detected. It saw the gold in the right place. It just it didn't move right because
We were too far.
Distance.
and also too
Yeah.
far.
Well, so couldn't you do a rotate at this point and then move it to the center of your robot? Otherwise, well, maybe you're doing that anyway. I get you turn, don't you? When you detect which of the 3 places it's at,
Mhm.
then you position the robot turns to the right place, right?
Yeah, and it
Okay.
does it in multiple steps to avoid hitting the other ones.
Yeah.
So, I think that one you saw it turn to the left
Yeah.
to clear, and then it turned back to the right, but it turned back a little too much because the robot was actually turned when he was holding it.
Oh, okay, gotcha. I gotcha.
It was in an IMU, so
Was-
it's relying on an IMU based turn
Yeah.
as to how many degrees it wants to go.
Okay.
okay,
So basically what we wanted to do is have different pluggable vision pipelines for each of our vision providers. So we talked about the TensorFlow model earlier that's provided by FTC, then our own convolutional neural network that we've yet to actually perfect, and then our Opencv pipeline. So as of now, we can switch between each of those 3, and then we also have a dummy integration, which basically if we know our vision is gonna fail, we just run dummy and it'll go to the middle.
yeah, we'll probably turn off the other ones by competition day as we figure out which one's the most reliable. But right now we're running OpenCV mainly.
Mhm.
And then this is a simple way to call our actual provider. And then we mentioned that the webcam is there to allow us to see the minerals easier. It's better than an Android phone because we can position it however we want and be more flexible with it.
And so these are some of the libraries we've used. We've been using OpenCV for just the pipelines, Euphoria for vision tracking, obviously Java and Android for the actual phones. Python and TensorFlow is how we attempted to train our neural network model, and then DL4J was we tried to experiment with DL4J instead of TensorFlow.
Now, we can talk a little bit about CartBot. CartBot is our motorized part. It works very well, but the problem with it is, at competition, you're only allowed to have one set of connected phones at a time. So we need a way to drive CartBot without having a second set of phones. So what we did was we changed around our robot controller app a little bit. So now we can run a joystick directly through the robot controller app onto CartBot. Do you want to try it?
Yeah, we have it. Do we have a USB hub?
Yeah.
So normally in a competition, we'd have one phone on the robot and another phone driving it as the driver station, connected to the joystick. And they communicate Wi-Fi direct, but you can only have one at the competition because of Wi-Fi interference.
Can you bring your own Wi-Fi router?
No.
Any Wi-Fi is
Wi-Fi
illegal,
direct. You can't bring extra Wi-Fi to the competition.
even like turning on the
They will
hotspot is
excommunicate
grounds
you
for.
for that.
Oh, really?
There's already too much. Yeah.
Like purple phones.
Yeah, but if you get your own private network, it might actually work and you get away from those
Yeah,
long
I
delays.
understand that, yeah.
Are you allowed to do any other frequency ranges?
So they govern what frequency ranges are allowed.
yeah, that's right.
So they are selectable for each pair of robot, each pair of phones. You could potentially get a different one. What they've done typically is these large competitions are double division events, which means that half of the robots run against within one group, and then there's another group. And what they've done is they've assigned channels to the different divisions.
Okay.
Could you use, since you're, for CartBot, I'm not talking about in the competition, but for CartBot,
Yeah.
which I assume is mainly used on the floor or possibly when you're with the judges, could you use Bluetooth?
So the rules say that Bluetooth is not allowed. So again, this is not, CartBot is not a legal competing robot.
Yeah.
But there's also rules saying you can only bring one robot to a competition. So we're kind of skirting the rules a little bit, but it's clearly a presentation. There's no way that it's illegal. It'll never fit
It won't
inside
fit
an
into
18
18.
HQ.
It won't
Yeah.
fit in 18.
Yeah,
Yeah.
not unless we get really aggressive with it. So they understand it's different, but they still, so when we've asked about it, they said, better not have that thing Wi-Fi enabled. And so that's why they created this hack. See, the underlying FTC app project that they provide, it inherently assumes that you have two phones. It always assumes there's a driver station. But what they did is figured out how to short circuit it so you don't actually have to have a second phone. And you can still drive it and start it up. You still need Wi-Fi source, I think. So I'm not sure that the hack is complete at this point.
It works.
Huh?
It works.
Don't you have to start it up using?
So you're allowed to do that in the pit.
Huh?
You're allowed to do that in the pit, and then after, we can disconnect from the laptop from the CartBot phone.
Yeah, all right.
So that's
What it does mean is that Wi-Fi is still turned on CartBot.
and then we turn it off after that.
So, yeah, so if we do it like in the parking lot, then we can get it into the right mode so that from then on it can be very control.
Okay.
Right? I mean,
So right now I'm plugged in directly into the.
Rush your driver back.
there's no
Yeah,
driver.
not the driver.
Yeah, he's not the driver.
Yeah.
So this is actually damped down quite a bit. This thing could hit 15 miles an hour pretty easy, and could actually go faster than that. And it will carry Karina up and down the street.
Yeah.
So,
And I think we can still do the
view tracking.
before you.
Yeah.
thing. It's state one, right?
So the point here is that you can use this API or this framework without having to have two different Android phones always connected. Although there's some benefits to having two phones, like with that telemetry stuff, and just controlling the higher level modes of the robot.
And this is again without any driver station. So yeah.
Cool.
So the cart, do other teams have carts or somebody?
Nobody has a motorized cart. Most people
We
just
haven't
have
seen a
a cart
motorized
that
cart
they
yet.
push around.
Oh, okay.
We're just flexing.
We've seen teams with monitors on their carts in the past, and big fancy LED lighting and stuff like that.
Is that a wheelchair?
No, it's not. So there's another competition called FRC. And the electronics that we're using for the drive system on this one are more like those. So they're sold by Andy Mark, and these are just, they're just bigger, regular DC motors.
Yeah. Is that an inverter down there?
Huh?
Is that an inverter?
It has an inverter on it as
Yes.
well, and we have a solar panel for charging. So it's a charging
Oh, okay.
solar type inverter, but yeah,
Oh,
we
right.
draw power off of it to like power the monitor during
Oh,
the judging
okay, yeah.
session. And it's powered by the same set of batteries that provide the power to the monitor.
Oh, okay, yeah. So it's like an MPPT tracker and maximum power point tracking.
So you can put the reticle on
Solar.
someone's button as they walk in, it just follows in.
That's right, yeah, that's the real plan, yeah.
Initially.
You have a,
Put before your trackers.
wear an orange pair of shorts that day.
It should be following people, following team members around.
Oh, one of the judges are out in the.
Oh yeah, I can do that.
Uh-huh.
Just tape it onto my back.
That's right, yeah.
Tape it onto the
We'll try
judges.
it.
We've done it before, so.
It's like a Nerf dart with like a RFID tag to sort of.
Alright, so that's the end of our presentation segment. Now we're gonna go into how we actually program one of our thingies.
So did anybody try to go and actually get Android Studio installed and all that
Yeah.
jazz?
I think a better question is who did it.
I tried to do it.
Then you got, it gets a little bit more complicated once you start getting into the actual build cycles.
Yeah.
So,
So
you know, we're not cloning.
It uses
Yeah.
Gradle and,
It did wonderful things
it's a
like
whole,
just
it's
hang
true,
up,
it's
you
a whole
know.
environment
It's
set
a
up,
non-trivial.
so if anybody is interested, we will, make ourselves available to an Arduino or two, so that we can sort of, cause I don't think right here is the best place to sort of debug the build environment. It is a full-on build environment, luckily it's free. There's nothing that we've had to pay for in it, including the starter framework. So we're gonna run the, we have the starter framework here?
Yeah, it's on GitHub. FTC has it published.
We got it up and running on Android.
Oh, does everyone have the FTC app downloaded? No?
Yeah, I have it downloaded. I gotta admit, I've never used Android Studio, so I didn't even know the extension for the the project.
Right.
And so, I mean, I did end up hitting on one that was the project.
You got it built all the way?
It's built.
Okay, no, if you got it built all the way, then that's great.
Okay,
Because
so-
you probably had to download a whole bunch of extra libraries,
Yeah,
right?
that's what they
You
said
did
in
that?
the email
Yeah.
beforehand, so.
Yeah, okay.
One in the
All right, so
morning,
we got one
one
person who's all the way through build? Is that it?
And I think I may be.
And then some of the older ones, when
Most of
we
it?
did the
Most of it.
FTC app,
Uh-huh.
the older ones.
Okay, hey
they had, like,
guys,
this
do me a
little-
favor, get together and let's end this video.
Hold on,
Because my
let's-
phone, I don't know if it can handle it much more. I can feel it getting warm.
Oh, getting hot? Yeah.
So go ahead, Kareem, get in there.
Oh,
This
you're
is,
the coach.
this is you guys.
All right.
All right. So end it with Iron Rain or whatever you're
Yeah, we
chanting.
don't really,
Yay!